where we do make some uric acid, but we make our uric acid. What does this look like?
Pure pie.
What? No, not tryptophan.
I was going to say one of the DNA bases.
One of the DNA bases. What kind of DNA base? Which ones have 2 rings?
Purines.
The purines. So in the metabolism of the purines, we do make some uric acid as part of the metabolism of purines. We don't make it from our amino acid nitrogen, but we do make it as we're breaking down purines. And so where do we get purines? Well, we do break down RNA, right, leftover RNA, but also we eat things made of cells. Those cells have DNA and RNA in them, and so we do get a substantial amount of nucleic acids as part of our diet. And so if you eat a big, heavy meal with lots of, shellfish is good for this, rich shellfish, then you get, as you digest that, you make uric acid. And if you have gout, there's a particular enzyme that is either less active or inactive in people with gout. And so the uric acid itself can build up to higher concentrations than it's supposed to in the system. And what did we just say about uric acid? What's it not? It's not water soluble, not very soluble at least. And so uric acid can begin to crystallize out of the system. And where it tends to do this for some reason are in the joints in your feet. And so people who suffer from gout, often the first symptom is their feet swell up. It's like they have sudden onset arthritic symptoms as these crystals come out in the joints of their feet. Have you seen the commercial? What is it? I can't remember the name of the drug. Where the guy starts out carrying the huge Erlenmeyer flask, and then he takes the medicine, and so his flask gets small enough that he can manage it. What is that?
It's like green liquids.
Yeah, it's all slosh, because he's having to deal with lots of uric acid. Anyway, so there are drugs to help deal with this. One of my friends, who used to be one of my racing friends, suffers from gout, and he did not know that he suffered from gout until he had one of these sudden onset issues. And so he had to stop going to the race because, let's see, what are the symptoms of gout? Achy feet. Now, if you're going to the Indianapolis 500, what do you have to do? You have to walk long distances, right? What else do you do around race time?
Cover your ears.
Cover your ears. That doesn't affect your gout.
Drink.
Drink a lot.
Let's go to that one last. You stand around. What else do you do?
I don't know.
You eat. You eat. Right? You have, right? You grill, right? Red meat. And you drink beer. So his doctor told him it was fine if he went to the Indianapolis 500 as long as he didn't walk long distances, didn't eat red meat, and didn't drink beer. Yeah.
That's not.
Other than that, he was perfectly fine going to the race.
Why is shrimp, why are shellfish, why do they have more of those?
They're just, I don't know, it's just that seems to be one of the foods that initiates a flare-up for a number of people. Red meat and shellfish, it's just so rich.
But aren't they the ones that can secrete the ammonia? Aren't they the ones that can excrete just the plain ammonia?
Right, but it's not the ammonia, it's the fact that they apparently have a lot of nucleic acids in their cells that you're breaking down. It's the nucleic acids that are the issues, right? The concentration of nucleic acids in those foods. So, anyway, that was my aside here. So, unfortunately, we're not going to get to talk about the metabolism of that uric acid. Okay? So, how do we deal with it? So we're going to go to the urea cycle. How do we deal with all that nitrogen? Overall, the urea cycle is this. You've got aspartate with a nitrogen in aspartate. But that nitrogen in aspartate, we will see, is handed to that aspartate from glutamate, which got it from all the other amino acids, right? So that nitrogen came from an amino acid. And then we've got a free amino group. But remember, where do we get that free amino group? Glutamate dehydrogenase, when you oxidize glutamate and then hydrolyze that, that can release free amino groups. So you've got this nitrogen that came directly from glutamate, this nitrogen that came from another glutamate, and glutamate got all that nitrogen from other amino acids. Okay, so that's the flow. Yeah.
Doesn't aspartate already have just an amino group because it's amino acid?
Right, but what would we have made aspartate from?
Okay.
Oxaloacetate. Right? So you've got oxaloacetate accepting an amino group from glutamate to make aspartate. Okay?
You said the other one comes from glutamate as well, right?
Right. Glutamate dehydrogenase. Remember our glutamate dehydrogenase reaction that we covered last time. Here, Kyle. Right? So glutamate dehydrogenase releases amino groups as free amino groups. No, I'm not going to go all the way back through there. Right? So both of these nitrogens originated in some other amino acid most of the time. Okay, so what are we going to do? Okay, we'll make this a little bigger. So here we are. Here is our amino group, right? So here's what I just said. Glutamate being oxidized, right? Glutamate being oxidized by glutamate dehydrogenase to release the free amino group, making alpha-ketoglutarate, which can, in the transaminase reaction, pick up another amino group from another amino acid. So this is cycling. So alpha-ketoglutarate to glutamate, nitrogen being transferred and released. Does that make sense? But now we want to activate that nitrogen and get started building our urea. So the carbamyl phosphate synthetase, which is carbamyl phosphate, is just one of my favorite molecules in biochemistry. I just think saying carbamyl phosphate is fun. Right? Because you get that. You got to get the amyl in there. Carbamyl phosphate. So the carbamyl phosphate synthetase takes ATP, carbon dioxide in the form of bicarbonate, and ammonia, and creates out of it this carbamyl phosphate. So a carbonyl from the carbon dioxide, nitrogen from ammonia, and a phosphate. So what have we created here?
Energy.
A high energy bond, right? A phosphoanhydride bond. A mixed anhydride bond. And this is going on in the mitochondria. Okay? So, we just made this carbamyl phosphate. Carbamyl phosphate is the form in which we feed this into the urea cycle. Okay? Now, the urea cycle starting material, right? Oxaloacetate was the starting cyclic material in the citric acid cycle. It's ornithine in the urea cycle. Now, if you look at ornithine, it's an alpha amino acid with an amino group. What does that look like? What?
Lysine.
Lysine. It looks a lot like lysine. What's the difference? Can you tell the difference, Evan?
It's not long
Is it one
enough.
shorter?
It's 1 carbon shorter. That's the only difference between ornithine and lysine. Is it's 1 carbon short of being lysine. Why didn't we learn this when we learned our other amino acids? No?
Not in proteins.
It's not in proteins, right? That's why we didn't learn it. It's not used to make proteins. When we learned our 20 amino acids, we only learned the 20 that we use to make proteins. So this is another alpha amino acid that is essential for this process, but that is not used for making proteins. Okay? So, the nitrogen here is going to be the nucleophile, right? To attack our high energy bond in a, what, Sarah?
Energetically favorable nucleophilic acid substitution.
You got it, right? And we make another amino acid that's unique to the cycle called citrulline, right? So citrulline, 3 carbons, nitrogen. Now the carbonyl and nitrogen, that comes from the carbonyl phosphate, right? So you can see that we're starting to build something that looks kind of like urea at the end of that molecule. Does that make sense? Okay. Now, here's where we get to some real fun. We're having some fun. Sorry, that was an old Steve Martin album flashback. 1978, maybe. Here at the boarding house in San Francisco, California. So, we've got this carbonyl. We know carbonyls are good electrophiles. The nitrogen of aspartate. We bring in another molecule of aspartate, right? The nitrogen of aspartate attacks that carbonyl and creates an imine functional group that we call arginosuccinate. So now can you see, if we cover this, can you see that, right? 3 carbons, nitrogen, carbon, nitrogen, nitrogen. That looks like arginine, right?
Wait, what just happened? Sorry.
This nitrogen attacked the carbonyl,
Oh.
and then
okay.
we eliminated water, and we were left with that. Okay? That makes sense? So, we get arginosuccinate. Now, we're going to break that in a lyase reaction. Right? A lyase reaction, 2 molecules come apart. We're going to get an elimination of arginine. And that elimination here, right, with arginine as the leaving group, that elimination creates fumarate out of the carbon that was aspartate. Right? Aspartate, fumarate. And now we have arginine. Okay? Now, just to sort of throw a wrench in the works. Remember, back in the dark ages of like last October, for those of you that took Biochem 1 last semester, maybe even late September, back in '63.